Welcome to Learn with Meshach. In this video, we're going to be talking about linear regression and be going from theory to practice. So these notebooks will walk you through the linear regression process, what it is, when to use it, how to train one in Python using scikit-learn. And this notebook is attached to this video and you can download it and also see the same code and be able to run the same code that I'm using in this video. So prior to this video, there's been another video on exploratory data analysis where I've explored this data to understand the data. And you can see that on the channel, it's showing somewhere on the screen. And you can also go to the channel videos and just see from the videos that we have on the channel. It's called Master IDA with Python. So I'll come back to this video. Now, what is linear regression? Linear regression finds the straight line or hyperplane that best fits your data. So it's a machine learning model that models the relationship between input X and continuous target Y. And your target could be anything. It could be crop yield, it could be house price. Then the input feature, you can have, for example, if it is house price, it can be the square meter of the house in terms of the size. It can be the location of the house. It can be the number of floors of the house. And all these things can be features to predict your house price. So the formula, you have this Y, which is your target variable, equals beta 0 plus beta 1 x1, beta 2 x2, plus plus beta n xn. So, and this beta, they are the coefficients. This BO is the intercept. So you can say the Y is the predicted value, the beta O is the intercept, and you have the beta 1 to beta n, depending on the number of input feature that you have for the modeling process. So what this is saying in terms of coefficient is how much does Y change per unit change in each of the feature. So how does it learn? It learns by finding the coefficient that minimize the sum of square errors between the predicted and the actual value, and this is called the ordinary least square. So each of these coefficients of each variable is looking for the best coefficient that when you get it, it will reduce the error between the predicted and the actual value. And linear regression doesn't stay in isolation, it has assumptions. So, and these are the assumptions. Number one is linearity. So linear regression, we always assume that the relationship between the feature and the target is linear. And the way to check this, you can do the scatter plot, the residual versus fit predicted plot, and we'll see this later in the video. It also assumes independence, that is, the observations are independent from each other. That is, observation A has no dependence on observation B. And that is another thing. And this will learn you through domain knowledge. You can do a Durbin-Watson test and different kind of tests to be able to see if it meets the assumption. Then normality of residual is another assumption. So it assumes that the errors are normally distributed. And we can see this through QQ plot and histogram of residual. We're going to see this at the end of the video. Then it assumes homoscedasticity. That is, the variance of errors is constant across the predictions. So when we do the residual versus fitted plot, we're going to see if it forms like a fan shape or if it's not a fan shape, if it goes exactly scattered around 0 and cluster around the 0. Then it assumes that there's no multicollinearity, that is, features are not highly correlated with each other. So it assumes that the fact that A is going up doesn't mean B is going down or that B is going up. So there's no multicollinearity. So you can see this through correlation matrix or the VIF score. I've done this in the exploratory data analysis where we did the correlation matrix. You can see that in the video I referred you to the other time. So what are the advantages and disadvantages? Number one is it is simple, it is fast and easy to interpret. So you don't need a lot of GPU process to be able to do it. You don't need a lot of compute to be able to carry out linear regression. It is very simple and it is fast. It works well when the true relationship is approximately linear. And you don't need to tune up a parameter necessarily. You can just use the vanilla version. It is a great baseline model to compare more complex models against. So whenever I want to start a machine learning project as a data scientist, I will first do a linear regression model. Then that will tell me a lot of things. I will do is plot the residual versus fitted, to plot the scatter plot, the active versus observed, and that just tells me how my data looks like. It will tell me I will be able to know quickly if my data is non-linear or if it is linear. And the disadvantage is that it cannot capture non-linear relationship without manual feature engineering. It is also sensitive to outliers. It assumes that features are independent and often underfit complex real-world data set. Because usually in the real world, the features that we are getting, they are not necessarily linear in the relationship that they have. So that is why, of course, you may need better models that is better than linear regression. And we're going to be having future videos that will be addressing this. Now let's move into the practical. So the first step is the data loading and preparation. And what we're going to be doing is importing our libraries. And for our libraries, the first thing we have warnings. And warnings is we are ignoring warnings that whenever we run a specific package, maybe to show a specific warning, but that warning is not necessarily going to interrupt the running of our code, but it may just be a lot of text that is showing on our output. And I just don't want to see that for now. In your real project, you can show the warnings without ignoring them. Then the next library, we have pandas for data frame manipulation. We have numpy for mathematical operation. We have matplotlib for plotting, seaborn for plotting. We have scipy for the statistics, and cargo hub to download the data set we need. So I'll run that, and that is done running. And here we're going to be downloading the data set, and the data set, use cargo hub the dataset download. I already have the directory of the data set, so you can see the data set on cargo. If I just copy this and I go and paste it into Google, and you can see crop your data set. Straightforward, I have it here. That's the data set that we're using. And I'll go back to the code. Now, when I run this, it will print the path for me. And so this is the path where the data is loaded into. And all I just need to do is the path and the name of the file. So the name of the file I need, you can see here, is called yield.df.csv. And we have UDS.csv, and I'll load that. So in the exploratory data analysis video, we already explored the data, and we've seen this column in the data that we don't need. It's just an index column that was a part of the data when it was exported because they did not drop the index. So we'll run that, and that will show us our data without that column. So you have area, item, area is country, item is crop, you have the year, you have the yield, you have average rainfall per year, you have pesticide in tons, then you have average temperature. Now we move to the next thing. And the next thing we want to see the shape of our data, and the shape will tell us how many rows, how many columns do we have, the data types. Then the df is null.sum is going to show us the missing values we have. So when I run that, you can see these are the column types. Then the missing values, we have no missing value in any of the predictor. So in the exploratory data analysis, we've also seen that we have countries in the data set, that is the area, that they have few occurrences in the data. So because of that, we're going to be dropping countries that have less than 100 occurrences. So to do that, we use country count to get the value count of the areas that we have. Then we use countries to drop to get the list of those areas that have less than 100. So to do that, we just subset based on country count, and we say less than 100, and we pass it into a list. Then the data frame would then be filtered using the countries to drop. So this tilde sign means for every of the row in the data that meets this condition of countries to drop, you should remove them. So the tilde sign is to remove. The reset index drop equals true. So when I run this, it's going to show us now we now have 71 countries, and we have 26,297 rows of data. So we move into our data splitting, that is the feature and the target split. So here, we're not going to be using year as our predictor, and we're not going to be using yield as our predictor because that is our target variable. So we say df.drop these two. If I was just having this single column that is just yield, I would not need to pass them into a list, but because I have more than one feature that I'm dropping, I'll pass it into a list. And axis equals 1 means choose what to drop from the column and not the row. Then y is equal to df, then we have the yield passed into it. So what this is saying is that our target variable is the crop yield. Then we now define what are our categorical columns, we have what are numerical columns. So using this, from the x, we say x and select the data types, include object. So the object, if you come back here, do you see? Area is object, items, we have it as object. So we want to extract them separately. So as categorical column. So we select object. So every of the feature we have that is an object data type will be extracted into a list. Then for numerical column, it will exclude any feature that is object. So it's just the opposite of it. So when I run, you see, now we have our categorical columns as area and item, and numerical columns as others that we have. So let's move into splitting the data for the model training itself. So we use train test split from sklearn.model selection. And we're going to be using stratified splitting. And why are we using stratified splitting? When you look at here, we have countries, we have about 71. We have crops also, that is items. These are crops. We have several crops. But if we split this data, there's a high chance that our training data may contain some features, some rows of data, that is, some categorical values that are not present in the test data. And we don't want that. So that's why we do stratification. However, the stratification parameter in the train test split uses just one column. It receives just one column. So how do we do that when we have two columns that we want to stratify as our baseline? Now, as a result of that, I'm going to be joining the two columns together into one column, just of course temporarily into stratified column. That's what I did here. So I'm joining the strings together. So it's going to be whatever I have in this column. For example, area, which one is what's area? So it's going to be area underscore whatever is in the item column. So if area is United States, for example, then item is potatoes. So it's going to be United States underscore potatoes. So that is what that is doing. Then we use our train test split. We are going to be splitting our data, the X and Y. We're going to be using 20% as the tests and 80% as the training data. So when I run this, you can see we have 21,037 rows for training, 5,260 rows for testing. Now we move to building the pipeline and to train our model. We'll be using the scikit-learn pipeline so that all processing and modeling happens in one clean step. So this will also prevent like data leakage. For example, if you don't have this pipeline correctly, you may have missing data point that is in training, that is not in test, or in test that is not in training. So we're going to be doing that using column transformer. We're going to be using our pipeline. I'll be using one-hot encoder to encode our categorical column. Because our categorical column is in text form, so we have this. You can say Albania, maize. So we need to encode them because our machine learning model, we only understand numbers. So to do that, we're going to be using the one-hot encoder. So we instantiate our column transformer, then we call it the preprocessor. That is the first thing we are doing. So the column transformer, we have transformer equals to, then depending on the number of transformation we want to do, we create a list for it. So here we are doing the category, then we say one-hot encoder, and we pass in the categorical column. Then remainder equals pass-through. So what this is saying is you don't touch the numerical variables that we have. That's what pass-through is doing. So use them the way they are exactly. And I'm going to run this model after. So for us to run it, we create this pipeline and we pass in pipeline using this pipeline library. Then we pass in our preprocessor into the pipeline. We pass our linear regression model into the pipeline also. So you see linear regression, we instantiate it within the pipeline. Then we now say pipeline.fit, then we'll pass our X train and our Y train to train our model. Then I'll run for us to see. So you see model trained successfully. Then let's evaluate. For evaluation, we make a prediction on the test data. Now we run this and that prediction is already stored in the YPRED, and we come into our sklearn, we import all our evaluation metrics. We are using root mean square error, mean absolute error, and R square. Then we then use the Y-test and the YPRED. So to do the evaluation, the Y-test, which is the original target value for this test feature, test input, we are going to be comparing the real value, which is the Y-test itself, with the predicted value. So we pass the same thing into each of these metrics and we run them. And you can see our MAE, we have 32,915. Our MSC, we have 53,000. Then our R square, we have 0.59. That's about 59% in terms of R square. And this doesn't look very good. What is MAE on the self? So MAE is just saying, on average, predictions are off by this many value. So you can see MAE showing us how off are we in our prediction. Then RMSE is similar to MAE, but what it does is it penalizes large errors more. So in places where we have large errors, it penalizes them more. So this RMSE helps us to really see that our model has a lot of large errors in some parts. Then R square is the proportion of the variance explained. If it is 1.0, then it is perfect. If it is 0.0, then it means no better prediction. So the model is not really learning as it should. But how can we improve this? Now, when I go back into our data set, you will see that here we have remainder equals pass-through. That means that our data set, if you look at how they look, now, here you can see the values in terms of the scale. You can see average rainfall per year is about 1,485. Look at the scale of pesticide, 121, and the scale of average temperature, you have 116.37. So when you look at the scale, you will see that the scale is very different. So when we use pass-through here, when we use remainder equals pass-through, the scale is affecting each other because one autoencoder will show your data set as 010101, the way it encodes them. Now you are comparing 01 with large scale of thousands. So that is affecting how the model is learning. That is why you will see if I remove this remainder equals pass-through. So what this is saying is don't touch the other numerical variables. Just make the prediction using the categorical variable alone. Then let's see if the accuracy will increase. So I'll run this again and I'll come back to the evaluation. I'll make the prediction and run the code. Now you see the accuracy jumped from 59 to 74. So what that tells us is that those other categorical variables, they are either not contributing so much to what the model is learning, or they are depreciating what the model is learning. They are affecting what the model is learning. But if we really want to see the impact that they have, if they really have meaningful impact, we can scale them, then add them back into the preprocessor. That is where standard scaler will come in. Now I will add the standard scaler here among the lists. So here within the list, I will add the standard scaler. So you see that now the numerical value, the standard scaler, and I'm saying scale the numerical columns. I want to see if it makes any difference. So I will run that again. Then I'll come back to the evaluation and run it. You can see it is not so different when I scale the data and I add it. That shows that the categorical variables in this data set are saying so much with respect to predicting the target variable compared to even all the numerical columns. And that is because we are using linear regression. So the model is not able to capture the contribution of those numerical columns as compared to the categorical columns. So, but I will still retain it there and not ignore it just in the data, at least for this learning process. So we move to our diagnostic plot. Initially, you see, I talked about the assumptions of linear regression, and we're going to be testing these assumptions by making this plot. So we are using matplotlib for this plot, and we're going to be plotting the actual versus predicted plot. So I'll just plot this straightforward, and you can see how the plot looks. So let me decrease this zoom so that we can see it clearly. Right, so you can see that now, that it started as if the lines are clustered close to the red line, but you can see that they diverge a lot. Not close to that, they're going away from the red line. That means the error is very high, especially by the time you are predicting above 200,000 yield. You can see the error is scattering all around. And this doesn't show a very nice pattern in our data set. So that shows that the linear regression, even though the accuracy might be 0.74, it is still not capturing the variation in the data accurately. So let's look at the residual distribution. So for residual distribution, it should be normally distributed and centered around 0. If it is skewed, then the model is systematically wrong for some observations. So we're going to see that by plotting this residual. So we have the histogram and the QQ plot to show us that. So when I run this, you can see that here, the model is skewed towards the right. So because normally, if the model is normal, if the distribution is normal, you're going to have minus 150,000, and around here, you're going to have up to minus 150,000. So we have all these values above 150,000. They are affecting how the model is learning. And you will see the same pattern here. So you see, by the time it was getting around 2 from here, it started going away from the line. And even from 0 here, it started dropping away from the line. And here it goes away from the line. So that is to tell you that this data set that we have does not meet the assumption of linear regression, even though the R square may be showing something like the model is performing well. At least 74% looks good in a way. But that is not the end. We are going to check the residual versus predicted value. So when I run this, you can see residual versus predicted value. Here, you see, this is not the shape that we want to see. This shows that there's no normality. It doesn't meet the assumption of linear regression. Because if this happened to be okay, we need something that follows this pattern. You see, this would have been a bit normal. If you see this kind of pattern, it would have been a bit normal. Although this is not perfect, but this is far better. You can see the cluster, you can see how they form, the cluster around the zero. You can see the zero line, the cluster around zero line, even though we have all these ones. But in our case, we have this. This doesn't look anyway like this. So it is far from it. So linear regression is not really the best model to handle this kind of data. Although there are things that we can do to make it better. But let's interpret the result. So how do you interpret? You say, is the R square high enough? If it is low, the linear model isn't capturing the underlying pattern very well. So in our case, our R square, we have 0.74. Well, it would have been nice if it was around 0.85 or 0.9 or 0.95 thereabout. It is not too low and it is not high enough also at the same time. So the model is not really learning as much as it should. Are the residual normally distributed? We concluded that the residual, they are not normally distributed. They are scattered around, not clustered around zero. And we can see also on the line, they didn't stay on the line. Here, they are very skewed. So we can also say that they are not normally distributed, so they don't meet the assumption of linear regression. So is there a pattern in the residual plot? For example, a random cloud around zero, like what we're talking about here. A curve or fan shape means assumptions are violated. So we can see the same thing. The assumptions are violated because it's just like a fan. In this case, it doesn't look like this. All right. So that shows that linear regression is not the best for this data. But if we still want to insist on using linear regression, we can log transform our target variable as it is rightly skewed. We can see, then we can use polynomial interaction feature. So we can create polynomial feature. That is by just, we can square or get the third polynomial term of a specific feature. And we can use that so that the model can capture nonlinear relationship. That's one thing we can do. But the best alternatives most times is just to try a different model. For example, random forest, XGBoost, CatBoost, and all others. And in future videos, we are going to be exploring other models. So using the same data set, we're going to be having a video on other models like random forest, XGBoost, CatBoost, and all others. And the last one is you can remove the outliers or investigate them more closely in the data. So this is the summary of everything in the video with respect to linear regression. I believe that by now you can download this code, try things out yourself, even use a new data set and follow the process and try to see. So I hope you've learned something. Like this video, subscribe, and also share the video with other people that would like to learn what you are learning. And if you have any question, feel free to comment. Thank you very much and see you in the next video.